our session today. So the workshop is titled An Introduction to Rasch. Can you guys see my slides? Okay, so it's a full screen, right? I just want to make sure that everything is in order before we start proper.
Yes.
Okay, thank you. So, so the workshop is titled An Introduction to Rasch Measurement for Education and Language Research. So this session is brought to you by the Learning Sciences and Assessment Academic Group at the National Institute of Education, Nanyang Technological University. So I'm Rong Chan, the moderator for this session, and my colleague, Dr. Wen Yun, and I are co-hosting the event today. So we are very honored to have our dear colleague, Dr. Vahid Ayadust, to conduct this workshop for us. So Dr. Vahid Ayadust is Assistant Professor in the English Language and Literature Academic Group at NIE NTU. He is also the Associate Director of the Global Listening Center. So his areas of expertise include language assessment, neural connection and comprehension, eye tracking and quantitative data analysis. He has also led a number of language assessment research projects funded by, for example, MOE Singapore, Michigan Language Assessment, Pearson Education, and Paragon Testing Enterprises. So Vahid is a member of the advisory board of multiple international journals and has been awarded the Intercontinental Academia Fellowship 2018 to 2019. So his YouTube channel, I would strongly encourage us to check it out when you have the time. Statistics and Theory has been awarded the Zhongcheng Social Media Award 2020, which recognizes exemplary and innovative use of social media. So without further ado, I will hand over to my dear colleague Vahid to start our workshop. Over to you, Vahid. Thank you.
Thank you. Thank you very much, Roshan, for the nice and kind introduction. And thank you for your invitation. So yes, I'm Vahid, and in this workshop, I'll be happy to talk about Rasch measurement and using the software package called Winsteps primarily. I should say that I have some slides, but I usually do not follow the slides that much. So I try to, for this presentation, I try to toggle through the slides, toggle back and through the slides in the software package, and I hope you will find it useful. For starters, let me share my screen first, please. Let me see what I can do here. Okay, this is share screen. All right, so does everyone see my screen now?
Yes, we can.
Very nice. So, and here is my slides, and I hope you can see my slides. Let me say, okay. So yeah, this is the introduction to Rasch measurement workshop. I would like to start off by giving you a very, very brief introduction to where Rasch measurement comes from and introduce you some resources if you're interested in learning more and reading more about the idea of measurement in psychological and social science research, as well as language. This is a book that I highly recommend. It's by Denny Borsboom, which is titled Measuring the Mind, and it has quite a few interesting chapters in it. I mean, all the chapters are very interesting. The first few chapters provide you with a historical perspective of measurement, and he talks about Rasch measurement, IRT, or item response theory, as well as structural equation modeling, and the very interesting coincidence that although Rasch measurement was very similar and is very similar to item response theory, it was being developed around the same time in a different part of the world than where IRT was being developed. And those guys who were developing these models were initially not even aware that other people in other parts of the world were developing very similar models. Ultimately, Rasch measurement became a very different, rather different approach to data analysis and test validation or psychometric validation of tests. And IRT became something like a statistical analysis. The differences of IRT and Rasch fall outside of the scope of this workshop, but if we find time later, and if you're interested, I'll be happy to talk about it a little bit. So I leave you with this slide and I move on to the second one. In this slide, I have summarized the different types of measurement models that kind of have to do with Rasch measurement. In other words, they are, in a way, extensions of the Rasch model, what we call the Rasch model, the model that was developed by this gentleman, George Rasch or Georg Rasch. The unidimensional models, which we will talk about today, are these. The Rasch model itself, which is the dichotomous one, and this is the one that was developed by George Rasch. The rating scale model, this is what we will discuss today. This is an extension of the first one, and basically it is very suitable for questionnaires or polytomous data, as you see in the brackets. So the rating scale model and another extension of the Rasch model, which is called the partial credit model. These are the two that we will talk about today. But whatever we discuss basically applies to many facets, Rasch measurement and the Rasch model itself. I've also here, provided a very short list of some IRT models, basically unidimensional IRT models, 1 parameter logistic, 2PL, and 3PL. And the reason why I have subsumed them under unidimensional model is, as I said, they're very similar in their mathematical representations. And then there are some multidimensional models as well, latent class models and their combination with Rasch, and finally the cognitive diagnostic model, which are also multidimensional, but they're used for diagnostic purposes. So I'm not going to go through any of these now. But I mean, if we find time, feel free to if you have questions, to raise them. And if I'm able to answer the questions, I'll be very happy to answer them. So getting started with preliminaries, the Rasch model was developed around 1960. And as I said, some people think, and I think they rightly think, that it's very similar to item response theory. And also it is somehow close mathematically to structural equation modeling. Okay, these can become philosophical and mathematical. So let's just get down to the brass tack, as they say. Rasch, the model that we want to discuss, is algebraically notated in this way, Pij. And that's simply how you estimate the probability of person I, person B to answer item D, person B with ability B to answer item D with difficulty D. So basically it's like a probabilistic representation of how likely you as individual I, to answer item J. And I think earlier I made a mistake there. That's item J, not item D. Item J, given that you have a certain ability level and given that the item has a certain difficulty level. As an example, if the item has a high difficulty, what is your probability if you're here and the item is up there? I hope you can see my me in the video here. So if you're here and the item is up there in terms of your ability and the difficulty of the item, what are your chances to answer that item correctly? And if it's the other way around, what are the chances to answer the item correctly still? Now, the one that the top sort of Rasch model we're going to talk about has one more parameter, and that's the FK. And that's basically the so-called the step parameter, or I mean, goes by different names. They call it step, they call it tau, and the difficulty of the threshold and those kind of things. Well, basically, if you have a questionnaire and if you are answering, for example, the questionnaire using a Likert scale, which is from 1 to 4, 1 standing for strongly disagree and 4 standing for strongly agree, each of these categories, 1, 2, 3, 4, also have a difficulty level. So in the rating scale model and partial credit model, we take into account those difficulty levels of those categories or scoring categories, and we basically factor them into the mathematical analysis of the probability. There are two more things that I'd like to state, and that's the idea of unidimensionality and local independence, which are the assumptions of Rasch measurement, the unidimensional Rasch measurement. And I'll talk about this by referring to the output of Winsteps. So I don't want to make it a kind of dry and theoretical discussion of what unidimensionality and local independence is. Rather, I'd prefer to talk about them in terms of the output of the Winsteps and how to make sense of it. And these are some links for you if you're interested to learn more about Rasch measurement. I highly recommend that you take a look at the winsteps.com. It's a website that has been around and is now currently being maintained by Dr. Mike Lineker, who is the developer of the Winsteps software, which we're going to use. Dr. Lineker is on the left-hand side, and his mentor or his friend, and I think his supervisor probably. I'm not sure about that, but I feel that's his supervisor, Dr. or Professor Benjamin Wright. On the right-hand side, they are two major figures in the field of Rasch measurement. There are many other figures, by the way. In the interest of time, I have not provided any lists and any names here. It will be countless, actually. So this is what we have on the menu for today, and I'm very happy to walk you through the Rasch software and tell you how to output these statistics or these measurements from Rasch analysis software. And also, I'm hoping that we will have time to do some breakouts, perhaps, because you know, if we run some analysis, it would be nice to immediately practice them on your own. I hope that Romchan can help me later to set up some breakout rooms, maybe for at least one breakout room or two, to give you some time to do some hands-on with some of your friends. All right, so far it was just a very brief introduction to Rasch measurement, and I hope that you've had a chance to download the software package Winsteps. If you have not, please go to this website and download it right now. So let me just see if I can open it and paste and go. Yeah, here you go. Winsteps is the demo version of Winsteps, and by clicking on this button, you can download quickly and easily. You don't have to have any passwords. Now, there is a limitation for this version, unfortunately. It's limited to 25 items and only 75 persons. So please expect some differences between the results of the analysis that I will carry out and the results of the analysis of yours if you're using this version, because the software only will take into account 75 persons and 25. I mean, for this presentation, we're going to have less than 25 items, so you won't have any problems here, but there might be limitations in terms of persons the estimation of persons measurements there, and also item measurements as well. So let's get started, everybody. Any questions so far? Good, no questions. I mean, feel free to raise your questions. I mean, it will be easier if I answer your questions along the way. So I have my Winsteps, Rasch. I hope you can see this. So I'm going to double click on it. So I suggest you do the same thing. Double click on Winsteps, and this window appears. Okay, good. Now, the first step towards Rasch measurement is, if you are using Winsteps, is to create your own input file. All right, and to create your input file, you have just a few very basic steps to follow. It's going to be a very easy start, actually. So if you are in the Winsteps interface here, you can see you should be able to see Excel RSSST. Click on this.
Rasch model, this is item response theory.
Sorry. Okay, so Excel RSSST is the type of input that you can use in order to create your Rasch input file. So if your data that you have collected is in an Excel sheet or R form, SAS, SPSS, Stata, text tab, well, these are 6 different formats. It's possible to create your input for Rasch measurement. But then again, if you might have other forms and you did not see on this menu, it's still possible. I suggest that you should convert them into one of these forms like Excel or SAS or SPSS, then just read them in. Now, the next step is to start off with our input building. And I hope you have had a chance to download the data that Rongcheng just shared with you. Well, there are several data sets. One of them is this data set here on the left-hand side, data set for tutorial. The other one is this sim call. The other one is sim DT, sim HY. It doesn't matter which one we use. So let's get, first of all, let's get started with this data set for tutorial. And before I go ahead, I want to open it really. It's an SPSS file, and I want to show you what is inside that SPSS file. If you even do not have SPSS installed on your computer, that's pretty fine, because Winsteps does not need that. It can easily open the file for you. So even if you cannot see what is inside the file, Winstep allows you later to sneak into the file and see what is there. So my SPSS is taking a few seconds to load. Please bear with me. Let's wait. Okay, I think it should be, yes, it's opening now. Anyway, this is an online version of SPSS, which is provided by NIE. So, every time when I want to open it, it takes some time, but it's never failed so far. So I'm expecting it will not fail this time. Yeah, there we are. Oh, there it is. Good. So we have 6 items, item 1 all the way to 6. And here is the data. As you can see, item. Okay, let's read the first line here for the first person. You see, this is person 1, number 1, who has given item 1 a 1, to item 2 2, item 3 3, item 4 5, item 5 4, item 6 a 5. So in other words, this is a question. This is how this person has endorsed these items. Let's say you have a Likert scale, as I said before, and you have strongly disagree, that's 1. Disagree, that's 2. Neutral, then then agree, that's 4. And then strongly agree, and that's 5. So when you read the item, then you decide whether you want to endorse this item highly. In other words, you want to say, yes, I strongly agree with this item. That is endorsing highly, and that's the terminology they use in Rasch measurement as well as many other fields, I assume. Or you might decide that, no, I really want to endorse it lowly because it's not what I believe in, or it's not what I think I can do, and so on. So I give it a 1. So that's your endorsement. Now I want to give you an example of some of these questionnaires. I hope I can find some examples for you. Or as I'm looking for the example, what you can do is just to think about any questionnaire you have seen so far. You might have a questionnaire in mind right now. I do remember I have one funny example. So any questionnaire that you have in mind could be quite useful. Okay, unfortunately, I cannot find it now. Anyway, no, never mind. For example, I love Rasch measurement. That's a questionnaire on any sort of questionnaire about liking for the Rasch measurement. I love Rasch measurement. Can you endorse it highly? Can you say I strongly agree? Or can you say I really don't love Rasch measurement? I'm neutral. I give it a 3. So you give it a 3. Someone else might say I really love Rasch measurement, and they give it a 5. And someone else says I despise Rasch measurement. I give it a 1. You know, so there are different people with different attitudes towards Rasch measurement. And at the end, what Rasch measurement will do for you is to help you quantify that attitude for you across different people, the attitude of different people. Okay, so these are the 6 items that we want to first use in order to start our Rasch analysis. So I'm going to go back to this little window here. This is still Winsteps, if you recall. Since this is an SPSS file, so I'm going to click on SPSS, and I hope you guys can follow me, please. Click on SPSS, and this window appears. Right, good. Now, in this window, you don't see anything. That's natural because we haven't done anything yet. Now we need to select SPSS file on this button. Yeah. Click and wait for the next window to appear. Okay, so this is my SPSS file, as you can see. I hope that you can find your SPSS file on your computer. And as soon as you did, just open it here at the bottom. And you see the button called Open. Click on that, please. And here is the rest of the operation. This Windows is now filled with a bunch of words and sentences. Well, we don't really need to read everything, but if you do want to know what's going on, let's go ahead and read everything. Just what I want to say is Winsteps does not read anything that has a semicolon before it. So it means that these pieces of information that are provided are only for you, really, and Winsteps doesn't care that much about it. So now the important part is this part. We have the variables. Do you recall? In the SPSS file, we had 6 variables, so you can see them here, and nothing else. Now, we have two rows here, item response variables and person label variables. under item response variables, I'm going to copy these these items, copy and paste it under item response variables. That's the first step to create Winsteps. Basically, that's perhaps the only step. Or you can just drag and drop. It's fine. I usually drag and drop it there. Right? So I'm going to undo what I did. I'm going to undo it because I feel that most often we have a large number of items here. For example, we have 40 items, 30 items, and you only want a few of them in your analysis. So that's not difficult. You can just copy and paste those items that you need under item response variables. That's one way of doing it. But if you feel that you're going to do several different Rasch analyses later, and in each Rasch analysis, you will just use a few of them. You don't have to create many different input files. You can create one input file, and later we can tell Winsteps that, hey, in this analysis, only analyze items, for example, from 1 to 4, and ignore the rest. Delete the rest. So I suggest that that's an easier way, really, because that kind of saves your time. In my opinion, that saves your time. Otherwise, you can just create separate input files. So let's just copy and paste or drag and drop the items under item responses. Make sure they will fall under item responses. Now, what about this line? Person labels. If you have something like gender or I don't know, anything that has to do with people attributes, and it will be in the SPSS file or in the Excel sheet, etc., you will see it under this area, and you can just copy and paste it under persons. Currently, we don't have that, so let's just move on. Okay, so now let's construct the Winsteps. Click on that construct. Did you see what I did? I'm going back to the column here, the button here. Construct Winsteps file. Okay, click on that, and there we go. We should just, you know, save it somewhere. So I've already created a file. I called it number1 dataset. I'm going to overwrite it. If you don't have that file, or you prefer to have a different name, that's perfectly fine. You can include a different label there. Yeah, put down the label for it, and then click save. Yeah, it's asking me whether I want to replace it. Yeah, of course, I want to replace it, but that's fine. All right. And then you should have this input file. This is going to be the input file which we are going to use for the analysis. Have you guys been able to create this? Does anyone need any assistance? Okay, no. Okay, so this file is quite, you know, ready to use, and you don't have to make any changes to it. Now, what we want to do is just to make sure that the number of items is correct. Yes, there are 6 of them. The number of people is 118. Let me look at my SPSS file. You might have 75, though, for the reasons I mentioned before. Yeah, I have 118. This is correct. I don't know how many you got there, but it could be those 75 or 118, depending on the version you're using. And 6 items. There are 2 more things here that I would like to draw your attention to. That's codes. You must be familiar with your questionnaire. You must check this code always. Your questionnaire should, if you have used a Likert scale from 1 to 5, you should only be able to see 1 to 5, 1, 2, 3, 4, 5. if you see anything else there, it would indicate that you might have a problem in your data. For example, if you suddenly see a 6 or a 7, that means you have miskeyed in a 6 or a 7 in your data. So before doing any analysis, you should go back to your data, find that miskeyed in number and replace it with the correct number. That's one thing you need to check. Number 2 is this line. You might still recall that I said anything that has a semicolon in front of it is not read by Winsteps, and this is no exception. Winsteps does not read this. Winsteps does not read this or this or this. So what does it mean? It means, let me go back to my slides. As I mentioned before, we're going to do 2 analyses. Rating scale model, which was developed by David Andrich and Anderson, and partial credit model. Partial credit model, I think by Professor Masters or Stone, maybe Masters. So what we're going to start with is a rating scale model. And I'm going to tell you what's the difference between them, but they're very similar to each other. In Winsteps analysis, it's very easy to either do a rating scale model or a partial credit model. By default, what's going to happen is that Winsteps is going to do a rating scale model for you. That's by default. So you can note that down somewhere so you'll not forget it. Winsteps does a rating scale model analysis by default if your data is polytoms, by the way. Now, if you want to get your Winsteps to do a partial credit model, what you need to do is, all you need to do is just to remove this semicolon like that. So then your analysis becomes a partial credit model. I'm sure that those of you who are not familiar with Rasch are asking, what is a partial credit model? What is a rating scale model? Don't worry about it, I'll explain that in a minute. I'm going to put back that semicolon and the space. The rest of the story is quite straightforward. We've got items 1 to 6, and this is the data. This is exactly the same as the data in my SPSS. So I don't need to make any changes or amendments to this file. Everything is fine. Most often we don't, if you just want to do a quick Rasch analysis, and I'm going to close it. So I don't want to save any changes. And since I'm done with this window, I can just close it. I go back to Rasch model. My Winsteps is still open. Well, actually, I can close it, and there's a cool way to do the Rasch analysis. You can close it too. Now, what I usually do is, this is the file that I created, the input file, right? Drag and drop the input file into Winsteps and check out what happens. Okay, Winsteps pops up again, and you see the name of control file in the version of Winsteps. My version is 5.0.1.0. Okay, so far you don't see any magic going on. So we can make the magic happen. Click Enter once, Enter on your keyboard. And Winsteps is asking if you need any extra specifications. No, we don't. And Enter again. The magic is happening now. Okay. So did you get this result so far? If you have, you must congratulate yourself, because this is the first step in Rasch analysis. Now, let's go step by step and see what we want to do in the analysis and what we want to get. So first things, I have done this. First things first, item reliability and person reliability are immediately outputted in this window. Can you see the window? Okay, so we have two sections here. One is the person section. The other one is the item section. What happened to this? Anyway. So person section, it was person, right on top here, and item. What is important in this part is the reliability index is right here, this 0.64. This is the index, 0.64. There's a problem in my Rasch software. I'm going to run it again. Drag and drop into. All right. So this is called iteration, and the iteration is done. We have got 18 iterations, I think. Yeah. So iteration is the estimation of ability and difficulty of people and the items, and also in this case the estimation of the step parameter that I mentioned before. Anyway, that's not a very important note for the time being. So we've got person reliability here and item reliability here. Traditionally, in traditional statistics, for example, in SPSS, we only look into item reliability. We don't look into person reliability. So I quickly do that in SPSS for you. It's in Analyze under Scale and Reliability Analysis. And I'm going to move all these items to items, alpha, statistics. I just want to get one statistics here. Item if skill if item is deleted, and continue. And okay, this is not Rasch, by the way. I just want to make a quick comparison between traditional reliability analysis and Rasch analysis. So Crumbux alpha is 0.57, is 0.58. Now it's close to our person reliability. Actually, it's person reliability, not item reliability. It's pretty close to person reliability. So a person reliability, therefore, is analogous to Crumbux alpha. But the difference is that in this analysis, instead of using raw scores, as is used in SPSS, measures or Rasch measures are used. So in my experience, oftentimes the Rasch reliability is slightly larger than reliability statistics in SPSS, that's Crumbux alpha. But the formulas are more or less the same. Anyway, so we have this, which is 0.64, which is honestly not very high. It's not a very strong statistic. Because for Rasch reliability to be high, you need to have something around 0.8 rather than something like 0.64. Is quite small. The other index is item reliability index, which is 0.99, which is pretty high. You know, the span of reliability is between 0 and 1, and the closer you get to 1, the better it is. In Rasch analysis, we aim for getting something above 0.8. Now, how do you make sense of reliability? For item reliability, this is the definition. Probability that items estimated with high measures actually do possess higher measures than items estimated with low measures. In other words, just to simplify it for you, reliability means whether the difficult items are really difficult and easy items are really easy in your analysis. By the same token, person reliability refers to the probability that persons estimated with high measures actually do possess higher measures than persons estimated with lower. So there is a real difference between persons of high ability and persons of low ability, meaning that we assume that in reliability analysis, some people have higher measures and some people have lower measures. And in the same way, some items have higher measures, that's they are more difficult, and some items have lower measures, that's they are less difficult and easier to answer as a result. So we're talking about the differences between people and differences between items. Now, there's another index which is called separation, as you can see here. For people or persons, it's 1.34. For items, it's 9.47. This is called separation, and it's a very useful index. Now, what does separation mean? Separation is the number of statistically different difficulty levels or difficulty strata that can be identified in the test items. Put simply, it means how many groups of items do I have within the 6 items that I measured? How many groups of items do I have which are different from each other with respect to their difficulty levels? In this case, I have 1.34 groups, which is basically just one group. If you round it down, you will get 1. It's not even 2. So it means that items are more or less similar, homogeneous in terms of their difficulty level. It means that they more or less have the same difficulty level. They cluster together.
Thank you.
They're clustered together. And what this means
you.
is, sorry, there's some background noise there. Okay, so what this means is, if you are having, for example, a test or an assessment, you might want to throw in some more difficult items because your items are quite easy. So this is one of the first takeaways for you guys if you are a teacher, and if the reliability of your items is low, you don't want to just quickly compute the total scores of your students and say, this is your score on this test. This is your score on this test. Now that doesn't make sense. The first thing we need to look at is, what is the reliability of my test? The other word for reliability is precision. In other words, with what precision am I giving you your total scores? In a sense, you can say that my confidence in the precision of these 6 items is 64% here. Yeah. Can you see that? 64%. So is 64% a high confidence level for me? I don't really think so. But despair not. If your reliability is low, it does not necessarily mean that you have a bad test or your data are bad or something like that. Sometimes it's because your people, your persons, are quite homogeneous and you can't do anything about it. Regardless of how precise your test is, these people are so much similar to each other that you cannot differentiate any levels, any reliable levels of ability among them. So that's another reason. The homogeneity of your people could be a reason for that. So the next thing that I'd like to stress here is, let's say you create a test and you administer the test to a group of students at the start of your teaching, then you give the same test to the students at the end of your teaching. Now, you might notice that in the second time, the reliability of your test might have dropped. I'm just guessing this can happen in some scenarios. Why does it happen? It's because that your students who were heterogeneous, first, there was a range. As you teach them throughout the days and throughout the years or throughout the semester, depending on how much you teach them, they become increasingly more homogeneous because they learn. And those of them who are already good, they just stay there on the top of the hierarchy. And those of them who keep learning start to catch up with the rest of those students. So in this scenario, what happens is that the reliability basically drops. Why? Because homogeneity increases. And that's a very interesting phenomenon. In this scenario, I wouldn't think that a low reliability is necessarily a bad thing. You know, we can argue further. You know, some of you might say, well, then you should create a more precise test in order to estimate the ability of those people more precisely so the reliability will increase. I do not necessarily disagree with that, but let's talk about that later if you're still interested. So let's keep this in mind, that reliability statistics is not that high, but for reliability for items is pretty high. It's almost 100%, which means that my confidence in the difficulty level of these items, or my confidence in the precision of the difficulty levels of these items is 99%. Now, how many different levels of difficulty can you find in these items for the people? Close to 10, close to 9. So this basically, what this means is that the items are quite different in terms of their difficulty level, but persons are not. Okay, so far, this is how we make sense of reliability and separation statistics. Do you have any questions? No questions. So these are some guidelines, tentative guidelines that I would share with you, right? So if you have something around 0.8, as I mentioned before, you begin to see two levels of separation. This is reliability, this is separation. So it's a good idea to see whether your reliability estimate is 0.8 at least. And if you see this, you often see that your separation levels are 2 or more. Always, actually, as a rule. Now, what else I have to share with you? I'd like to recommend this paper that we wrote and is published in Language Testing. It's basically about everything that has been published so far in the field of language assessment about Rasch measurement. And we have provided some recommendations and guidelines about everything, including reliability analysis. So for further reading, I suggest this. It was a paper we worked on for about 2 years. So I think we found quite interesting stuff there. Anyway, so this is the first step. Now I'm gonna run the analysis again. It's taking some time. Okay, good. We have, and this is the analysis. All right, the same statistics is replicated so far. Now, what is next? After reliability, and these are some guidelines there, which I mentioned before, we move on to estimations of item parameters, difficulty, ability, logits, and those kind of things. So let's get started with that. This is more fun, perhaps. Okay, let me check the chat box. I think there are some, okay, good. All right. There's some questions. Krishnan is asking, mostly applicable based on Likert scale. Oh yeah, so Ranchang has already answered that question. Well, this is applicable to both Likert scales and non-Likert scales. So if you have a test which consists of things like 0, 1, 0, 1, those kind of things, you can still do it. That will become a Rasch measurement, basically, what we call the Rasch model analysis. Likert scales or non-Likert scales, anything basically can be submitted to Rasch analysis. Okay, step 2 is to go through the output tables. Click on output tables. You see 3 columns here, or 3 blocks. The first block is about items. The one in the middle is about persons. And the last column is about persons and items. So let's focus on items first, these guys. The first thing I would like to immediately look at is the right map, number 12. Click on the right map. So you can note this down for your future reference. The first thing to look at is number 12 first. Click number 12. And here is my items and people. Okay, so you might be asking, what is this? This is called the right map. And right map is basically in honor of Professor Benjamin Wright. Together with Mike Lineker, they created this map. So it's named after him, right map, if you're interested to know, a little bit of history. Now, in this right map, we've got persons on the right and the left-hand side and items on the right-hand side. What does that mean? It means that we have arranged people based on their ability level alongside a continuum. So the most able people are these guys here on top. The least able person is this little dot here. So every hash mark is 2, and every dot mark is 1 person. Now, you might have a different format for your analysis, by the way. It's because, especially if you're using the trial version, and the reason for that is that it can only analyze 75 people. So don't worry if you have different shape of the right map in your analysis than mine, or if the reliability analyses that I shared before are different from mine. That's because your sample is smaller. Now, the most difficult item here is number 2. Basically, since we have a Likert scale, we don't use the word difficult often. The best word to use is endorsable. This item is very difficult to endorse. So it has a low endorsability. That's why it's very difficult. So let's say, actually, I found the items I was looking for. Look at these items. I can easily kill a man, and someone might say, I can easily kill a woman too. So what? Now, personally, I myself cannot really kill anyone, so I would give it a 1. So this means the endorsability of this item for me is very low. As a result, it's difficult to endorse. So endorsability is low because I can't kill a man. Now, there might be someone who just, enjoys killing people, and he or she might say, I give it a 4 because I can easily kill people. That's why I ended up in prison. So I give it a 4. I am often, so another question, I'm often so angry that I want to punch anyone around me. I don't think that probably is true for me. So I still give it a 1, depending on how people treat me. I often try to keep my cool and just keep it at 1. So this item is still difficult for me to endorse highly. And as a result, a 1 for me is the best option. Now, some of you might say, well, when I go to a Rasch class, basically, I jump from 1 to 4. So this item suddenly becomes easy to endorse, and I give it a 4. So endorsability of that item for you goes up, but for me, who gives it a 1, is low. This is what I mean by item endorsability, and so on. I can easily kill a woman. This is another version of item 1. I hate everyone, and things like that. So this is what I mean by endorsability. Therefore, item number 2 is very difficult to endorse. The second difficult item to endorse is item 1. The third difficult item is 3, and then 5, and then 4 and 6, which are more or less the same. They're not exactly the same. This is a little bit of a kind of imprecision in this map. Later on, we can look at the statistics. They might be exactly the same. They might be slightly different. On the left-hand side, you can see people. They've also been arranged based on their total scores, to put it, very roughly. The total score of these people are the highest. The total score of these people are low. This guy is certainly lower, and this guy is the lowest. So this person kept giving 1 or 2 or 1 or 1 to all items. The other thing we need to take into account is these two M's, M here and M on the right side and M on the left side. The M on the right side is the mean of items. M on the left side, on the other hand, now I think you should be able to guess, it's the mean of, excuse me. So the M is the mean of persons on the left side. Now, what do you notice here? The M of items, the mean of items, is lower than the mean of persons. What does it tell you? Well, the first simple thing that it tells us is that on average, items are easier compared with person's ability. So if this were a test, we would have interpreted in this way. The items or my test is too easy for my students because of the mean of the students and the mean of the items. And you can see that visually here, M and M. Now, the other thing you see is that there's a big gap between Q3 and Q5. In fact, you have 2 clusters of items. One cluster is right at the bottom, which includes 4, 6, and 5, this cluster. Another cluster is items 1, 2, 3. So cognitively speaking, these items are not easy to endorse, those on top. And again, cognitively speaking, the items at the bottom of the hierarchy are easy to endorse. So my speculation is that those items are measuring something else, probably. It's just a speculation, honestly. I might be totally wrong, but I speculate that those items on top are measuring something that is cognitively more demanding than those items right at the bottom. Now, of course, we need to provide to get more information about these items and see what they are and what we can do about it. Now, I don't want to stay on this map for a long time. Just the other thing I wanted to say is that we've got S's, S on the right side and S on the left side. S on the left side and the right side, S stands for standard deviation. So I assume that you know what standard deviation is. It's a standardized yardstick, and it consists of 1 unit of measurement. As you see, 1 and 2 items, 3 items basically are falling within 1 standard deviation above and below the mean, and 2 items here and 1 item here, altogether 3 are falling within, this T stands for 2 standard deviation. They're falling within 2 standard deviations above the mean and below the mean. You see, you have got 2 T's, T and T. For Pearson's, we also have the same thing, mean 1 standard deviation, 2 standard deviation above the mean, S 1 standard deviation, and T 2 standard deviations. Now, this person, or these 3 people, whoever they are more than 2 standard deviations above the mean. In a sense, they're outliers. And if they are students who took a test, it means that they are way above the rest of your students. So they are fast learners, they are ahead of the rest of the group, or they're better in whatever they're doing, or something else. You know, we can make these speculations. And in the same way, you have some students like this guy and this guy, certainly, who probably need immediate help. Of course, this is a questionnaire. I mean, the questionnaire might just be asking about the attitude. But if it were a test, this student and this student would still be within 2 standard deviations from the mean. Then I think, because it's between S and T, so it's within 2 standard deviations below the mean. So I think they might have a problem, these guys, in whatever we are teaching, if this is a test. So let's just wrap it up. This is the right map, and it gives you some basic information about your items on the right-hand side and persons on the left-hand side. Finally, this is called logit. This is a scale, pretty much like centimeters. You see, it's like a ruler. And rulers, you have got, I've got centimeters here on my ruler, 1, 2, 0, 1, 2, 3, 4, all the way up to 30 centimeters. Let's assume that logits are also like rulers. So it's like, if you fall on number 1, you are 1 logit able. If you fall on number 2, you are 2 logit able. The word is logit, or log odd units, something like centimeters. So let me go back to logits and see if I have. Yes, here is what I mean. Logits and log odd units is the expansion. The acronym is logit. And I think that's more or less, I talked about these. Okay. So I'm going to pause here. Any questions? No questions. So I would like to continue by going through the output tables. The first thing I have outputted so far has been number 12. Now, what I would like to do is to go through fit order. So item fit, this is another important piece of information for me. I'm going to click on this, and this table will pop up. So we have a lot of information in this table and the rest of the tables under this. Okay, but don't worry about it. I'm going to highlight those pieces of information that are important for us. First of all, let's read this table. These are our items. Item 4, 6, 1, 2, 3, 5. So this is very easy. Now the total score is 500 on the first one. That's if you add up all the scores that my 118 students, you see 118 students, gave to item 4, they add up to 500. So they endorse this item very highly. Compare this with number 2. As you recall, item 2 was very difficult. Do you remember? It's because that people gave it a lower score altogether. Gave it, on average, a lower score. So we get 288. Okay. Now this column is measure, and this refers to the ruler that I mentioned before. So the units are logits. For example, the second item number 2, which is the most difficult one, has a logit of 1.29. So it falls on top because its weight is higher. So it falls on top of the hierarchy, 1.29. Whereas an item like item 4 falls right at the bottom because it's minus 1.30. Okay, so minus and plus is just one way that which we represent the item difficulty or item endorsability. What you need to take into account is just the size of measure. The larger the size, the more difficult the item, or the more difficult the item to endorse. So it's obviously number 2, which is the most difficult item to endorse. Okay, now there's another thing which is called model standard error. What does that mean? Basically, standard error is the precision of the measure. For example, for the first one, I'm gonna write it down here. I think this will make it easy. Okay, I hope you can see my Word document, and here you go. Good. So what does standard error of measurement mean? It means that this is the difficulty. So minus, I write it here in the middle, minus 1.30 is the difficulty of my item, right? Now, if you're asking me how certain you are about the precision with which you measured the difficulty of this item, I would say I am this much confident about it. This item is plus minus 0.13 difficult, which means that if I could assume a range, it will be between minus 1.30 and here, plus 0.13 on this side and 0.13. So it indicates that the actual item difficulty falls between 1.43 and minus 1.43. So the actual item difficulty falls between these two. Is it a very wide range? I don't think that this is a very wide range. So what does it mean? It means that the item difficulty has been estimated with a good amount of precision, and I shouldn't be that much worried about it. There's good precision in my analysis, therefore. Okay, so for the rest of the items, you can make the same kind of conclusion. You can say that the item difficulty of item number 6 falls between minus 1.20 plus minus 0.13, and so on and so forth. Okay, so this is the precision with which we have estimated the items, and there is no rules here for SE. If you're asking me what is a good SE and what is a bad SE, there's no rule, but based on my experience and as a rule of thumb, the smaller this SE, the better it is. Something around, really, I can't really establish a criterion, but this is not too bad to me. I have sometimes seen SEs which are much larger than this amount, so that's a little bit of a red flag, but this is not a red flag. Okay, so far so good. Now we've got 2 important fit statistics, and if I go through fit statistics, there will be 2 more things to discuss for today, and that will be all. So let's talk about fit statistics. What is fit? There are 2 types of fit. One is called infit, and one is called outfit. Okay. Now, I want to remind you that SE is about precision of difficulty, okay, or ability of people. In this case, it's difficulty. Of course, you can look at ability too. I can look at it later, but for the time being, it's about difficulty. So it's about precision. It's not about whether this minus 1.30 is wrong or right, or it's not about whether this minus 1.30 has been affected by something lethal or something useless or not. And there is a statistic that it is called fit, infit and outfit. So I give an example. If you are a test taker, let me go back to the right map here, right, yeah. If you are a test taker and if you are here on the map, your ability level is -1. And if you want to try answering question 2, right? If it's a test, if it's not a questionnaire, let's say if it's a reading test. Now, do you have a high chance to answer this item? No, you don't, because it's way above your ability level. Look at the distance of question 2 and you. All right, so I expect that you will not answer this item correctly, or you will not score highly on this item. Now, what if you do? What if in reality, this is my expectation, but in reality, my expectation may not come true. You might have cheated. Who knows? You know, the student who's taken the test might have just looked over the shoulder of his friend and say, okay, that's the answer to this item. I didn't know, but I just managed to get away with it. So I cheated and I got away with it. That's one possibility. So my answer, although it's correct, it doesn't belong to myself. It doesn't show my ability. It shows how smart I am when it comes to cheating. Or another option, another possible scenario is that the items were not created with much care. So some students who were smarter and who were test-wise could basically guess the answer. Does their answer show their ability level? No, it doesn't. It just shows how smart they are in doing something else other than what the test is measuring, right? So we need to have some statistics to show whether the student's performance is actually because of their ability level or because of something else, like cheating, like guessing, like the low quality of the items, and so on and so forth. One way of doing this is to look at the fit statistics. Okay, so infit and outfit are those statistics that are useful. Now, infit is described in this way: is an inlier sensitive or information weighted fit, which is more sensitive to patterns of responses to items targeted on the person and vice versa. All this means is that if you are, this is the hierarchy again, and let's say you are here, and your items are Q1, Q2, Q3. Let's say some items are here, and some items are right on top, Q9, Q10. Okay, so if you answer these items in an unexpected way, unexpected would be that if you miss a few of these items, because these are in your range of ability, they're pretty much around you, so you should be able to answer the questions correctly. But if you miss a few of them, that's a little bit of a problem. There's a little bit of red flag there. So what is happening is that this is captured by infit. That anomaly, that unexpected pattern is captured by the infit. And I want to stress this because it's important. Some people misunderstand what infit is. Infit is a statistic that captures the anomaly around you in this region. On the other hand, outfit captures the anomaly for outliers. That's why we call it outfit, meaning that if you happen to answer all of these items or some of them correctly, then the outfit has the ability to capture that anomaly. So the definition is infit means it's an inlier sensitive, and that's what it means. It's lying in. Inlier is here. So it's inlier sensitive, meaning that it's more sensitive to patterns of responses to items targeted on person. Items that are targeted on person means the items that are consistent with the ability level of the person. On the other hand, outfit means outlier sensitive, those outliers, more sensitive to responses to items with difficulty far from the person. So like I said, it's more sensitive to people who are far from this person, here or here, even at the bottom. Example, question 11, question 12. So now what you expect here to happen is that this person should answer these items correctly. There might be quite a few items, but this person doesn't answer those items correctly. Maybe he misses on half of them. But that's strange because he's expected to answer them correctly. So what's happening here? It might be that this person found that these items are so easy that he doesn't even have to think about it. So he just closes his eyes and just chooses A, B, C, D if it's a multiple choice questions. Or he doesn't read the items at all. He says, oh, what are these simple items? I'm not going to even read them. So what happens is that you will get an inflation in the outfit statistics. Whenever the outfit or the infit inflate, it's like your blood pressure that goes up. If you have a high blood pressure, there's a problem there. So in the same way, if the outfit or infit, any of them really, infit or outfit, goes up, we're looking at a problem. What problem is that? And how do we identify that problem? First of all, remember, what I mean by that is that we need to consider a range for infits and outfits, outside of which we're looking at a problem. Just like the blood pressure that I said, if it's too low, it could be problematic. If it's too high, it could be problematic in a different way. Now, there are two types of infits and outfits. One is called mean square and the other called Z standardized. So mean square fit and standardized fit. For mean square fit, I mean, there are many different ways of saying it. One very rough and I should say it's imprecise, but just for simplicity, I'm going to mention it. One rough and simple criterion is this: if your infit mean square falls between 0.5 and 1.5, you're fine. Between 1.5 and 2, that's bad. Above 2, it's terrible. I don't know how to represent it with a shape. Does that make sense? It's like an extraterrestrial creature with two mouths. But anyway, that indicates if it's above 2, it's really bad. If it's between 1.5 and 2, it means something is going on there. There might be a problem. But if it's between 0.5 and 1.5, it's pretty fine. Now, this is like I said, it's imprecise. If you want to get more precision about fit, infit, and outfit, here is what I'd recommend. For multiple choice questions, this is the range 0.8, 1.2 for high stakes multiple choice questions. For low stakes multiple choice questions, 0.7, 1.3. For rating scales like surveys and questionnaires, 0.6, 1.4. And for other circumstances, these apply. I leave this here. If you like, you can take a photo. And or if you would like to read more about this, you can take a look at the paper I showed you before, this one. And sorry for shamelessly advertising my work, but I thought it might be useful to some of you. Okay, so I'm going to go back to the fit statistics. If we assume 0.5 to 1.5 is a good thing, all of these items, they're infit mean square values. Can you see? Basically meet that criteria. And here, all the way down meets that criteria, and that's pretty fine. But then we've got Z standardized, and I should tell you that Z standardized is useful. However, make sure that your sample size is something between 100 to 250 to use Z standardized. Why is it so? Because if it's below 100, Z standardized gets inflated easily. And if it's above 100, Z standardized gets inflated easily too. So even some people would say that you don't even need to pay attention to Z standardized. You don't even need to care about it. But if you're curious, this is how you can interpret it. And it should fall between -2 and +2. So look for anything that is lower than -2 or above -2. Do we have anything like that? Luckily, we don't. That's the good news. All right, everybody. Rongchan, can I ask you how much time is left for the rest of the workshop?
We have about 7 minutes left. Wahid, it's a 1.5 hour workshop.
Okay, sure. So, okay, this is infit and outfit mean square values. Thank you, Rongchan. One last thing that I wanted to mention here is the question of unidimensionality. As I mentioned before, unidimensionality and local independence are important. So let me wrap up everything I've told you so far. I've talked about reliability and separation, infit, outfit, infit mean square, outfit mean square values. I've also talked about the map, the right map. Now, these make sense only if you have any evidence, supporting evidence, that your test is unidimensional. Unidimensional, where is unidimensional? Okay, I don't know. Okay, unidimensional. What do we mean by unidimensionality here? I don't go to too much details, so I just quickly show you how unidimensionality analysis can be carried out. All right, so I'm in Winsteps. I go to output tables. This is a unidimensionality analysis, so I go to table 23 and click. This window will probably pop up. If you have an earlier version of Winsteps, the window might be different. But here you don't have to change anything. Just click OK. And this window appears. At the interest of time, I don't want to go through this with too much details. This unidimensionality analysis simply indicates whether
your test items or your Likert scale items are measuring one thing or different things. Now, how do we know if we're measuring one thing or two things? You see, we have this table here. The first thing we need to look at quickly is the raw unexplained variance. And that's unexplained variance in the first contrast, and then the second contrast, etc. Look at this statistic. If it's roughly around 2, it's most likely, your scale is most likely unidimensional, and whatever you have estimated so far makes sense. If it's above 2, which is the case here, around 3 or so, your scale is most likely not unidimensional. And you need to find out what items are causing multidimensionality and separate them from the rest of the items and run the analysis again. What does it mean? It's a very important concept. It means that, for example, if you're a teacher and you're administering a test of grammar or reading or whatever to your students, and if you run their unidimensionality analysis, provided that you have a large enough sample size, something around 40 is just good enough to get decent Rasch measurement statistics. So you run the analysis and you find out that your test is not unidimensional. The implication that it has for you is that you cannot add up the scores of your students on the test items and give them a total score, because you will be adding up apples and oranges. You're adding up two things which are not probably relevant to each other, unless you have a strong justification. And now, it's very obvious that in this scale, I don't have unidimensionality. Why? Because the eigenvalues are larger than 3. And I'm sorry that I go through this very fast, because I want to cover it at least to give you an idea about unidimensionality. If you have questions, we can talk about it later. If there is any time left for Q&A. But 3 is obviously indicating that there is something wrong in my data. So I scroll down, just let's forget all of them and go to this table, is table 23.1. I obviously have 2 clusters of items. Items 4, 6, and 5 clustered together, and items 3, 1, 2 clustered together. So it indicates this is a usual principal component analysis. Those of you who are familiar with factor analysis and principal component analysis think they would know what this thing is. So basically what has emerged in this principal component analysis is 2 components, which are 2 groups of items, which are different. One group loads on the component positively here. You see its positive side, 0.8, 0.7. And one group is on the negative side, minus 0.6, minus 0.7, minus 0.8, etc. And this simply indicates that we have 2 things going on in this scale. What I should do is to run the analysis on items 3, 1, and 2 separately from items 4, 6, and 5. That would be the best. That's one thing that I could do. Number 2 is that it might be the case that in a Likert scale kind of questionnaire, these items must be reverse coded first. So, you know, sometimes the items are negatively worded. Sometimes items are, some are negatively worded, some are positively worded. The answers of the students to those items cannot be added up. You need to reverse code those items that are negatively worded first. For example, I like apples. I don't like apple juice. These 2 items cannot be added up. Why? Because the second one is a negative item. So if I give item 2, I don't like apple juice, if I endorse it as 1, this 1 has to be reverse coded into 5. You know, reverse coding is like that. This is the last thing I want to say. So if you have a scale like 1, 2, 3, 4, 5, if you want to reverse code it, it's going to be 5, 4, 3, 2, 1. So you need to change any 1 that's given by students to a 5, 2s to a 4, 3 and 3 will remain the same because it's a neutral point. 4 will be converted to 2 and 5s will be converted to 1s. And I think that's probably the end of the time that I have, Rangjan.
Yes, on the dot. Thank you so much, Vahid. So
Thank you very
yeah,
much.
thank you so much for your generous sharing. So let's put our virtual hands together to thank Vahid for an enriching morning. So thank you for your generous sharing. So on this note, we will stop recording. And if it is possible, I would like to invite